So let's discuss section 6.5 now. And you notice that the title here has kinetics, and right next to it, no relation to delta G. So they really want to remind you that the delta G, or the Gibbs free energy value that you find, really doesn't tell you anything about the rate or how fast a reaction is, or what we'll call the kinetics of the process. Um, Even though we do know that when we have a negative delta G value, our process is product favored and spontaneous in that forward direction. Um, so delta G tells us nothing about how fast a reaction will occur. That's the main point here. Um, but we can consider that some spontaneous processes are fast, right? So energy is released quickly with explosions. And then other processes that are still spontaneous still will happen eventually, even if it takes, millions of years. Things like diamond turning into its, preferred in standard temperature and pressure state of graphite here, right? So we have something that takes a really long time, but is still spontaneous. So let's look at kinetics in this section here. So there are 5 factors that we'll consider when we talk about kinetics. So these reaction rates depend on the things listed here below. So things like the concentration of reactants, right? Higher concentration of, say, reactant A generally leads to an increase in collisions. Right? So this would give us potentially more product formation if everything else is in the right range. Something like our activation energy, right? We need to have that in order to reach our transition state, right? The top of our um, energy diagram, right? We need our molecule to have the right amount of activation energy, right? From reactants to products here. Oh, it's a P. We see this value that's commonly designated as the activation energy. Then the reaction can progress to product. Temperature affects our rate of reaction, right? So when molecules have more kinetic energy, they're moving faster, again, more collisions, so more collide at faster temperature. There's also the geometry, right? The molecular geometry, or what we can call the sterics. Um, Things like steric hindrance will be discussed later on, or reasons that certain shapes of molecules prevent reactions from happening. So the shape. And then, of course, if you remember what a catalyst is, this lowers activation energy and then increases rate, right? So this is what a catalyst does. So of course, kinetics or rate will be affected by that last part there, that catalyst. So let's move on here to something else that may look familiar, something called a rate equation, aka a rate law, and then how we determine what order a reaction is. So hopefully this is a review for you. If not, go back and review what rate laws are and the form of the rate equation that we have here. So rate, so whatever unit you use for rate, right? So commonly things like molar per second, a rate of appearance or disappearance, can depend on a rate constant. So this K value, and then the concentration of the starting material. So this is a very generalized rate law, and this can, correspond to either a forward or reverse reaction, because we have different rate constants for reactions in equilibrium for their forward and reverse, and we also can be affected by, the reactants in either direction, which would be products, depending on which way you look at it. And then the order, right? We mentioned this as well here. If there's only one reactant listed, there will be a first order reaction. So let's take a look here at some examples of this. So we could have our rate equation here. So rate is given by some constant K times the concentration of reactant A raised to the X power. So that's how many molecules need to react. So if it's 1, it could be to the first power. If it was 2, it would be something that looks like this over here. So we have, in general, each of the reactants raised to a relative power. So for a first order reaction, we could say that if the concentration of A is doubled, that would make the rate go twice as fast, right? So the rate would be doubled. Then when we have a second order reaction, such as in the middle here, we can see that we have two reactants that need to have just the right energy and collide in just the right orientation. So all these factors being what they are, if we increased the concentration of one of these reagents, one of these reactants, we would again double the rate. But say we have a third order reaction where we have A squared here, so A to the second power, and then molecule B is just raised to the first power. If we now double the concentration of A, we actually will quadruple the rate. So hopefully that was mostly review for you, these rate equations, and then first, second, and third order reactions, what they look like, and then how, if concentration is altered, the rate will be affected. So you should know those concepts. And then we see here kind of a breakdown of each of those factors that affect our rate. So we've talked about this in the past, this activation energy. This is another way of saying what's the barrier between our reactant and when they can turn into our product, right? When these molecules change. So this activation energy, this difference can be considered a barrier between the reactants turning into product. So this is the minimum amount of energy that is required for when a molecule hits another molecule for the reaction to happen, right? So we need them to hit each other, to collide, and also have the right amount of energy. So another concept that we can, expand upon here with this activation energy is if this activation energy, say, is at this point here, we would have, this graph shows us the number of molecules under the curve here. So these are all molecules that do not have enough energy, that have lower than the activation energy, but this blue filled in region here, these have enough activation energy. So EA is reached by these molecules. But they tell us here, right, if we increase the activation energy, right, so say we moved EA up here, we have less molecules, right, that have enough energy to react. So therefore, that would lower our reaction rate. So we can see here that kind of summarized between these two slides, we have a lower activation energy versus a higher activation energy. So the lower results in a faster rate, and the higher activation energy would cause the reaction to move slower. Right, so this is good to note here. Temperature, how does temperature affect our reaction rate? Well, we'll go back to our bell curve here, and you notice that in lower T and the blue curve, so the lower temperature curve, there's more molecules in this region below the activation energy. Then the higher temperature here, we can see all these molecules under the curve, right, at the higher temperature have the required activation energy. So at higher temperature, more molecules have the right energy to produce the product. So again, higher temperature, faster reaction. And then we saw steric consideration. So this term steric hindrance, or the reaction being hindered by the shape of the molecule, the molecular geometry of the compound. Things that are easy to access, right? When they bump into each other, bonds can form faster than if there's these bulky kind of groups, so say we had a molecule that looked like this, right? We have these bulky groups around where the new bond needs to form. So it might not happen as quick as if we had a molecule that looked like that, for instance. So if the reactive conformation of this compound is high energy, so what that means is the The conformation means different shapes, different bond angles within the molecule, might be at a higher energy, and that molecule won't stay in that higher energy as long. So again, the probability of collision happening at the right energy and the right orientation is low. So we'll get into this a little bit more in the next chapter. So we looked at, lastly, when catalysts or enzymes, if we're talking about biological reactions, are utilized. These will speed up the rate of a reaction without actually being used up, right? So a catalyst, it just speeds up the reaction by lowering the activation energy. And as a result, it commonly changes, right, the pathway here. So we can see that this is a single transition state process in blue without the catalyst, and then the red curve shows us multiple transition states, right? 1, 2, 3 transition states. And then we also have multiple intermediates. So even though we lower the activation energy so the reaction will go faster, we will return our catalyst. It will not be utilized, and it just changes the pathway of the reaction and allows it to move faster by lowering activation energy. So that's it for section 6.5. We will continue with these energy diagrams and kind of comparison of kinetics to thermodynamics next time.